First, let's see how steam is formed in the water tubes of the HRSG. This steam-generating zone is often referred to as the evaporator section, as this is precisely what happens. Heat is transferred through the tube walls, and the water is evaporated into steam. In order to promote natural circulation, the boiler tubes are arranged vertically with the hot gas passing across the tubes in the horizontal direction. The exit gas is directed into the bottom of the stack. But what causes this natural circulation of steam and water in the boiler tubes? Let's look at the circuit. Feed water is fed into the steam drum, and from here it passes down through downcomers to the lower drum or header. From this point it is distributed to the bottom of the tubes known as risers. Water then rises through these tubes and picks up a large quantity of heat absorbed from the hot gas. Some of the water is turned into steam, so forming steam bubbles. The steam bubbles rise and eventually burst to form a column of steam in the upper section of each tube. As we all know, a column of steam weighs much less than a column of water. Thus we have a disequilibrium. The cooler water in the downcomer descends, while the hot steam and water mixture rises. So we have a continuous natural circulation of water down from the steam drum into the header and up the water tubes. As the water rises in the boiler tubes, it is evaporated into steam, and the steam is returned to the upper portion of the boiler drum. Steam from the drum then passes into the superheater, and we'll be talking about this in a moment. The rate of water circulation in the tubes depends upon the heat input from the gas. For example, if the exhaust gas quantity and temperature increase, say due to an increase in gas turbine load, then there will be a greater transfer of heat to the water and steam circuit. As a consequence, more steam is evaporated, and in order to replace this, more feed water will have to be supplied to the HRSG. The feed water flow is automatically controlled, as we shall see in a moment. You'll recognize this natural circulation as a similar process to that in a combustion-fired boiler. Because of their similarity, you will often hear the HRSG referred to as the boiler. A common way of pronouncing HRSG is HRSG. HRSGs are also built utilizing forced circulation. In this arrangement, the water is pumped through the evaporator section instead of relying upon natural circulation by gravity, and thus the evaporator does not have to be built vertically. This simplified diagram shows the typical arrangement for a forced circulation HRSG. The bank of tubes are arranged horizontally, and the discharge stack sits directly on top of the HRSG. As before, feed water is fed into the drum. From here, it's pumped at a controlled rate into the evaporator tubes, where steam is formed by absorbing heat from the turbine exhaust gas. The steam returns to the drum, and from here it is passed through the superheater. An economizer is often provided to heat up the feed water before it enters the steam drum. This is located in the gas path downstream of the evaporator section. The objective of the economizer is to usefully absorb as much as possible of the heat from the exit gas before it is discharged to atmosphere. This diagram shows us a vertical arrangement with an economizer in the natural circulation type HRSG. Here we see the basic construction layout of a natural circulation HRSG showing the major components. The inlet duct is carrying gas from the gas turbine exhaust at temperatures as high as 1,100 degrees Fahrenheit or 600 degrees Celsius. For this reason, the steel casing must be well insulated so as to avoid heat loss to atmosphere. On certain units where high gas inlet temperatures are anticipated, water walls may be installed around the inside of the ducting in order to recover some of this heat and reduce heat loss through the casing. Casing insulation continues right on through the HRSG until it enters the stack. Even at this location, where the gas temperature is, say, 300 to 400 degrees Fahrenheit, 150 to 200 degrees Celsius, we could still suffer considerable heat loss. The tube banks which provide the boiler heat transfer surface are installed in a modular form. For example, the economizer section is shop-built and shipped to the site in one unit like this. It is then connected to the appropriate feed piping on one side and the steam drum on the other. And here is the modular evaporator section where steam generation takes place. Finned tubes are usually employed throughout the HRSG in order to increase the heat transfer surface area on the gas side. We want to extract as much heat as possible from the hot gas. Here we see the bank of superheater tubes which add heat to the steam before it is finally discharged from the boiler. More about this later. The steam drum forms an important part of the steam and water circuit and has several functions. Let's take a closer look inside the drum. Feed water is fed into the drum under pressure from the feed water system. It enters the drum through this distribution header, which runs the whole length of the drum. In this way, the incoming water is evenly dispersed. The flow of feed water into the drum is automatically controlled so as to maintain the level about halfway up the drum. From the bottom of the drum, this water feeds the downcomer tubes, which supply water to the evaporator section. Steam returning from the evaporator section is fed into the upper part of the drum, but it is first passed through separators. The function of these separators is to separate out any water droplets that may be contained in the steam. We want the steam leaving the drum to be as dry as possible. After passing through the separators, any water is directed into the lower part of the drum, while the dry steam passes out to the superheater. There are various other piping connections into and out of the drum. A chemical feed connection allows us to inject certain chemicals from time to time as part of the boiler water control. Also, as part of boiler water control, a blowdown connection is fitted. This allows us to continuously discharge a small amount of water from the boiler drum in order to reduce solids. Both of these items will be discussed later in this tape. Gauge glasses are normally fitted at each end of the drum to provide a visual indication of the water level. As we have already pointed out, this level will normally be maintained at the midpoint. Vent connections are fitted on top of the drum. These small 1-inch connections allow us to discharge air to atmosphere while the boiler pressure is being raised. Once all air has been expelled, the vents are closed, and they remain closed during normal operation. The opposite action is necessary when shutting down the HRSG for an extended period of time, say for maintenance. As the HRSG cools, the pressure will eventually fall to atmospheric. The vents should be opened at this time. Safety valves are normally fitted on top of the steam drum to operate and discharge steam to atmosphere in the case that excess pressure builds up. Okay, so far we've looked at the generation of steam in the evaporator section. Before we move on to look at the superheater, let's take a break. For now, please switch off the tape and review this material in your workbook. Steam collected in the drum from the evaporator section is known as saturated steam. It is at saturation temperature. Now, what does this mean? At any specific pressure, the value of saturation temperature is the same numerical value as the evaporation temperature. We all know that the evaporation temperature, that is, the boiling point of water at atmospheric pressure, is 212 degrees Fahrenheit, 100 degrees Celsius. This is the temperature at which water starts to evaporate into steam. However, in order to convert all of the water into steam, a lot more heat energy must be added. This is known as the latent heat of vaporization. During this process, the temperature remains the same, 212 degrees Fahrenheit, until all of the water has become steam. This point, when 100% evaporation has been completed, is known as the saturation point, at the saturation temperature, 212 degrees Fahrenheit. Any further addition of heat causes the steam temperature to rise. The actual value of evaporation temperature and saturation temperature varies with pressure. The higher the pressure, the higher the saturation temperature. Actual values are given in the steam tables. For example, if the pressure in the steam drum is, say, 1500 psi, about 100 bar, then the temperature of the saturated steam is about 600 degrees Fahrenheit, 315 degrees Celsius. This sounds like a reasonably high temperature, but we certainly cannot use saturated steam in the steam turbine. Why is this? Well, the problem is, as the steam is piped to the turbine, there is bound to be some heat loss, and this would cause a very small quantity of the steam to condense, so forming water droplets within the steam. This is where the term wet steam comes from. The steam passes through the turbine at such high velocity that even the tiniest water droplet could cause serious damage to the turbine blades. So it's necessary to add further heat to the steam and raise its temperature above the saturation level. This has two advantages. First, it ensures that the steam remains dry, even with some heat loss through the pipework. Second, by adding additional heat and raising the steam temperature, we can pack more energy into each pound of steam and so perform more useful work. This additional heat above the saturation point is known as superheat. Typically, on our HRSG units, the steam outlet temperature will be about 950 degrees Fahrenheit, 510 degrees Celsius. That is 350 degrees Fahrenheit or 195 degrees Celsius above the saturation temperature of 600. This may be referred to as 350 degrees Fahrenheit or 195 degrees Celsius of superheat. Superheat is added in the superheater section of the HRSG. Steam from the top of the steam drum is fed into the superheater inlet header. From here, it passes through the bank of superheater tubes, which all discharge to a common superheater outlet header. From this common header, the superheated steam is piped to the steam turbine. If other HRSGs are operating in parallel to supply the same turbine, a stop valve would be located at each outlet. This will allow us to take any HRSG out of service while continuing to operate the steam turbine on the other units. On large HRSGs, the superheater is usually divided into two sections, primary and secondary, with headers between them. The secondary section produces the higher temperature steam because it is located upstream in the higher temperature gas zone. We can control the temperature of the steam leaving the unit by spraying in a small quantity of feed water into the steam through a de-superheater at the primary outlet header. The steam here already contains a considerable amount of superheat and is therefore dry. The de-superheater water is quickly evaporated into steam, but in doing so, it reduces the temperature of the steam entering the secondary superheater. The quantity of water injected into the D-superheater is controlled by monitoring the final steam temperature as it leaves the HRSG. Steam temperature control is often referred to as attemperation. It becomes very important where high gas temperatures exist from the gas turbine or from a fired section. The vertical superheater shown here is known as the pendant type because it is supported by and hangs freely from the inlet and outlet headers. This allows the superheater great flexibility in accommodating expansion, particularly during startup or rapid load changes. During startup, the headers must be vented to atmosphere. This is to allow any accumulated condensate to boil off during the startup and so allow free flow of steam through the superheater tubes. But why is this necessary? After a shutdown, any steam remaining in the superheater tubes will eventually condense and actually block flow of steam through the tubes. This could cause overheating of the superheater tube metal during startup if gas flow and temperature are not well controlled. The only way to dispose of the condensate is by evaporation as heat is added. The superheater vents and drains should be left open until steam flow is established through the tubes. That is, either by placing the steam turbine on load or by directing the steam through the bypass to the condenser. In order to assist in draining condensed steam from the superheater, a horizontal arrangement is sometimes employed like this. In this case, the lower header drains can be opened during startup to drain off any accumulation of condensate. Safety valves are located on the superheater outlet header. These safety valves are usually set at a lower value than those on the steam drum. And this is to make sure that the superheater safety valves open first and so maintain a flow of steam through the superheater. In addition to this, the setting must allow for the pressure drop through the superheater, which may be in the order of, say, 60 psi 4 bar. But what could make the steam pressure rise and cause the safety valves to open? Well, steam pressure is actually controlled by a balance of two functions. The amount of energy extracted by the HRSG from the exhaust gas, that is, energy in. The amount of steam energy being extracted from the HRSG, that is, energy out. In normal operation, the two work in equilibrium. Energy in equals energy out. The steam turbine plus any other process steam demand absorbs all of the steam energy being produced by the HRSG. The main steam pressure is really determined by the resistance to flow downstream. For example, the turbine throttle valve may be adjusted to, say, reduce steam flow into the turbine and so maintain steam pressure upstream of the valve. In contrast to this, most combined cycle units are operated with the throttle valve wide open, so that the only resistance to flow is presented by the turbine blading. In this situation, if the heat input to the HRSG decreases, then main steam pressure falls. We already discussed this sliding pressure method of operation in the previous tape. Let's now consider what happens if the steam turbine trips. The steam stop valve closes and the flow of steam is immediately halted, so that energy output from the HRSG falls to zero or close to zero. But we are still at this instance receiving heat input from the flow of exhaust gas through the HRSG. The result of this unbalance is that the steam pressure rises immediately and causes the safety valves to lift. In fact, if the safety valves did not lift, some components of steam piping and boiler tubing could be ruptured by the rapidly rising pressure. We can already see here an advantage of the gas bypass around the HRSG. In the case of a steam turbine trip, the exhaust gas can be immediately directed to the stack, thus diverting flow from the HRSG. With no gas bypass, it would be necessary to trip the gas turbine unless 100% of the steam output can be bypassed to the condenser. We've been discussing arrangements for the superheater, but some HRSGs are fitted with a reheater as well. You'll remember that we discussed the function of the reheater in the previous videotape. Constructionally, the reheater is similar to the superheater. It consists of a bank of tubes, and these are located in the same zone as the superheater, so as to produce a hot reheat temperature of, say, 1,000 degrees Fahrenheit or 540 degrees Celsius, the same as the main superheater temperature. The reheater may be split into primary and secondary banks with a D-superheater located between them to permit control of hot reheat temperature. The reheater tubes are lighter in construction than the superheater because the internal pressure is much lower, usually about 400 psi, say 28.5 bar, as compared with, say, 1500 psi or about 100 bar for the superheater. So far in this tape, we've been looking at a single pressure HRSG only. Now, before we move on to look at multiple pressure units, let's first take a break. For now, please switch off the tape and review this material in your workbook. In order to extract as much heat as possible from the exhaust gas, most HRSGs are constructed with 2 or even 3 different pressure sections. Let us first look at the physical arrangement. Here we see the exhaust gas coming from the turbine and passing directly through all sections of the HRSG, finally exiting to the stack. Here is the high-pressure steam drum. Here, the IP steam drum, and here, the LP steam drum. In this particular construction, the de-aerator is built on top of the LP steam drum. Note on this arrangement that various inspection doors are provided so as to allow access into different areas of the HRSG. You must always make sure that the access doors are well sealed so as to prevent leakage. Remember, the gas inside the HRSG is under a positive pressure, and any leakage to atmosphere will result in a heat loss. In some units, a seal air system is employed. Seal air fans provide a positive air pressure at around 10 psi or 0.7 bar. And this is arranged to provide a seal around the inspection doors. It is far better to have air leaking in than hot gas leaking out. A particularly difficult area to seal is that of the dampers. Various damper arrangements are employed. We may have, for example, a separate inlet damper to the HRSG, a separate exit damper from the HRSG to the stack, inlet and outlet dampers on the bypass, a bypass damper to a separate bypass stack. This eliminates the need for an exit damper from the HRSG. In some cases, the bypass damper and the inlet damper are combined into one single unit. The damper directs the gas either through the HRSG or through the bypass. These dampers are extremely large and considerable force is required to operate them. Pneumatic or hydraulic actuators are employed for this purpose, and these are activated from the control system. Ideally, the dampers should be able to modulate, that is, operate in the partially closed position, as well as fully closed or fully open. It is most important to prevent leakage around a closed damper. For example, when the unit is in service, it would be most inefficient to waste gas through the bypass. By contrast, if the unit is out of service for maintenance, it would be difficult and indeed hazardous to work on the unit with hot gas seeping through. For this reason, sealing air is usually employed around the dampers. Large sealing air fans are provided for this purpose. Okay, so let's take a look at the internals of this HRSG. First, look at the LP section. In this unit, we have a condensate preheater, which heats condensate on its way to the de-aerator. On this particular HRSG, the de-aerator is of the integral type. It is built into the HRSG. The steam drum acts as the de-aerator storage tank. De-aerated water from this drum or storage tank supplies the HP and IP feed water pumps, as well as the LP evaporator. So in this arrangement, all of the feed water, which is demanded by the HP, IP, and LP sections, must be fed into the de-aerator as condensate. The condensate pump is designed with sufficient pressure and capacity to feed enough water into the de-aerator. Remember, steam generation does take place in the LP section, and it is this steam which is supplied to the de-aerator to remove the oxygen and other incondensable gases. The level of water in the drum or storage tank is maintained by the feed water control valve. Here we have the IP economizer feeding water into the IP drum. Here is the IP downcomer, the lower headers, and the IP steam generation tubes or risers. Steam from the IP drum is fed into the superheater, finally exhausting for intermediate pressure usage. Here we have the HP economizer, feeding water into the HP steam drum. Here is the HP downcomer, the lower headers, and the HP risers. Steam from the HP drum feeds through the primary and secondary superheater, finally exiting to feed the turbine. In this particular boiler, we also have a primary and secondary reheater located in the same zone as the primary and secondary superheaters. The superheat and reheat attemperators are located between the primary and secondary sections. On this HRSG, we have a duct burner, which is designed to burn natural gas or light distillate oil. As you know, the burner can be fired when it's required to maintain the gas temperature into the HRSG, while the gas turbine operates at low load. In fact, in some installations, a forced draft fan is installed so as to permit firing and operation of the HRSG even when the associated gas turbine is shut down. Of particular interest in this HRSG is the catalytic converter. The objective of this device is to reduce NOx emissions to atmosphere. You will remember that we discussed this in an earlier videotape. By injecting ammonia into the gas stream, the converter changes most of the nitrous oxide into harmless nitrogen and water vapor. This is known as the SCR process, which stands for selective catalytic reduction. One particular disadvantage of using the SCR system for NOx reduction is that it will not be available when the HRSG is bypassed. And this would mean that the gas turbine would need to be shut down if the HRSG was inoperable. Of course, one way around this problem is to install a steam or water anti-NOx system for use on such an occasion. For the SCR process to function correctly, it must take place within a very narrow band of temperature, and it is this which decides the location of the converter. This temperature consideration introduces a problem when the gas turbine load is reduced and the gas temperature subsequently falls. The use of fired burners to maintain gas temperature helps overcome this problem. Operation of the fired burners is automated, but operator attention is still required. When the HRSG is in service, make sure that the burner equipment is always ready for operation. Ensure that the fuel system is available and ignition and control circuits are ready. When the burners are actually firing, make sure that the control system is functioning correctly to maintain the desired gas temperature. The gas temperature is continuously monitored at various points throughout the HRSG, typically gas inlet to the HP superheater, gas inlet to the HP evaporator, exit gas to the stack. Generally, the exit gas temperature to the stack is in the range 280 to 300 degrees Fahrenheit, 140 to 150 degrees Celsius. If at any time the temperature falls below that level, we may run into problems with condensation from moisture contained in the gas. The moisture may come from anti-NOx injection or from the combustion of oil or natural gas. Condensation on the ductwork and other components is likely to cause severe corrosion, particularly if even small quantities of sulfur are present in the gas stream. Normally, the HRSG is designed to keep exit gas temperatures above the dew point, about 260 degrees Fahrenheit or 130 degrees Celsius. But this may be difficult to achieve during startup. For this reason, in some installations, the condensate preheaters are bypassed during startup. We'll be talking more about this in the next segment, which looks in detail at the condensate and feed system. But for now, it's time for a break. Please switch off the tape and review this material in your workbook. As we've mentioned before, the most common arrangement of combined cycle for power generation uses a condensing steam turbine. After exhausting from the steam turbine, all of the steam is condensed and collected in the hot well at the bottom of the condenser. From here, it is pumped through the condensate system into the de-aerator. The pressure of the condensate pump must, of course, be sufficient to overcome the pressure in the de-aerator, plus the losses in the piping system. We have already noted that typically the steam pressure in the de-aerator is about 100 psi or 7 bar. So we would expect the condensate pump discharge pressure to be about 150 to 200 psi or 10 to 14 bar. The temperature of the condensate in the hot well will normally be around 100 degrees Fahrenheit, 40 degrees Celsius. In order to increase the cycle efficiency, it is usual to increase the condensate temperature to about 300 degrees Fahrenheit, 150 degrees Celsius, before feeding this into the de-aerator. The first stage of heating is performed by passing the condensate through the gland steam condenser. In this heat exchanger, the condensate picks up heat from leak-off steam from the turbine shaft gland seals. This raises the condensate temperature to about 125 degrees Fahrenheit, 50 degrees Celsius. From here, the condensate passes through a series of heaters in order to bring the temperature up to the desired level, say 300 degrees Fahrenheit or 150 degrees Celsius. In some installations, feed water heating is employed using steam, which is extracted from the turbine. You will no doubt be familiar with extraction heaters as employed in conventional steam power plants. 2 or 3 closed tubular heaters are installed with condensate passing through the tubes and steam flowing over the outside of the tubes. The condensed steam from each heater is returned to the condenser hot well to become part of the condensate stream. In recent combined cycle installations, condensate preheaters are installed in the gas path downstream of the LP evaporator. These preheaters take the place of steam extraction heaters. This method has the advantage of utilizing heat from the exhaust gas. But we have to be careful not to lower the exhaust gas temperature too far because of the possibility of corrosion. So we may find in some installations a certain amount of steam extraction heating, plus some condensate preheating by exhaust gas. Now, let's see what happens in a de-aerator. In our typical example, we have condensate being supplied at a temperature of about 300 degrees Fahrenheit, 150 degrees Celsius, and steam being supplied at a pressure of 100 psia, 7 bar, and temperature of 328 degrees Fahrenheit, 160 degrees Celsius. As the water enters the de-aerator under pressure, it is sprayed into the tray section. From here, the water droplets pass over trays, all the time mixing with steam, eventually falling into the storage tank. The steam and water become mixed, with the steam condensing and the water temperature increasing close to saturation. The result of this agitation and increase of temperature enables most of the incondensable gases, such as oxygen, nitrogen, and CO2, which are dissolved in the water, to be liberated. These gases are expelled through vents at the top of the de-aerator. Some steam may try to escape with the gases, but this is condensed in a vent condenser, which employs incoming condensate as the coolant. De-aerators have been used for many years and have been developed to be highly reliable. We expect the feed water coming from the de-aerator to contain as little as 2 parts per billion of oxygen. But why do we go to all this effort to expel oxygen and other gases which may be dissolved in the condensate? Well, it's for protection of the boiler internals. The presence of even very small quantities of oxygen in feed water can lead to severe corrosion of the boiler tubes. This factor is so important that chemical means are also adopted to keep oxygen out of feed water. And we'll be talking about this in a moment. So now we have the de-aerated condensate sitting in the de-aerator storage tank, ready to be fed into the HRSG. Actually, from this point on, the same water is known as feed water, as it passes through the feed water system. The de-aerator and de-aerator storage tank are usually located at high elevation in order to provide the positive suction head to the boiler feed pumps, which are normally on the ground floor. For a multi-pressure HRSG, there will be feed pumps operating at different pressures, typically LP, IP, and HP. In each case, the feed pump discharge pressure at full flow must be higher than the associated drum pressure plus system losses. In each of the circuits, a feed water control valve is installed to regulate the flow of feed water and maintain the correct level in the drum. On each feed pump, a recirculating line is installed so as to maintain minimum flow through the pump, in the case that the feed water control valve closes, perhaps due to high water level in the drum. The recirculating valve opens automatically when the flow through the pump falls below a minimum value. It recirculates water back to the de-aerator. The feed pump is such an important part of the system that 100% standby is normally provided. This means each pump is duplicated. The standby pump should always be available and ready to start automatically in case of failure of the running pump. On many installations, a warming line is fitted so as to make sure that the pump is indeed ready for immediate operation. The warming line allows a very small quantity of water to bypass the check valve. That is, it allows a small quantity of hot water to flow from the discharge into the pump. As we saw in the last segment, where an integral de-aerator is used, an LP feed pump is not required. The condensate pump itself provides this service. Some installations utilize the same feed pump to provide feed water for both the HP and IP sections. In this arrangement, the feed pump is usually a dual pressure pump, with IP feed water being tapped off at an intermediate point. Of course, both pressure systems still retain their independent feed water control valves. So let's see how this total cycle is kept under control when there is, say, an increase in heat input from the exhaust gas. Perhaps the gas turbine has increased the load. The first result is an increase in steam generation and steam flow to the steam turbine. But what is happening in the HRSG? Well, as more steam is drawn off the HRSG, then more feed water must be supplied. So the feed water pump draws more water from the de-aerator storage tank. This level starts to fall, and this in turn opens the inlet control valve so as to demand more water from the condensate pump. As the condensate pump obliges, the level of the hot well will begin to fall. But just about this time, we have additional steam being condensed, and so increasing the level of the hot well. Now, during these load changes, as you would expect, there will be, of course, some fluctuations. Actually, the hot well contains a relatively small amount of water, so the level could change quite drastically. This is controlled by other means. First, if the hot well level falls, then makeup is provided from the condensate storage tank. Remember, the condenser, including the hot well, is under quite a high vacuum, say 2 inches of mercury back pressure, that is 28 inches of vacuum, or 1 bar. When the control valve opens, water flows from the condensate storage tank into the hot well. The reverse will happen if the hot well level starts to rise. In this case, condensate from the discharge side of the condensate pump will be sent back to the condensate storage tank. So in this system, we have continuous circulation of steam, condensate, and feed water round and round the system, with only minor fluctuations in levels of the hot well, de-aerator storage tank, and boiler drums. But of course, there will be some small amount of leakage from this system, perhaps through pump glands, leaking valves, and so on. In practice, we expect the leakage to be less than 0.5%, but it still adds up to a considerable amount of water over a period of time. Makeup to the system is provided from the condensate storage tank. But where does this water come from? Well, of course, we know we cannot use ordinary water for makeup. After all, the condensate, which is condensed steam, is as pure as you can get. And so, consequently, is the boiler feed water. Because of this, the makeup must also be high-quality water. And this is usually produced in a demineralizer. Now, this is opening up another subject. The chemical control of feed water and boiler water itself is a very important part of boiler operation. And we'll be talking about this in the next segment. At this point, we want to take a break. Please switch off the tape now and review this material in your workbook. In this segment, we'll take a look at control of the HRSG. Of course, most of the control actions are performed automatically, but the operator must be aware of the current status and also be prepared to take manual action if this becomes necessary. Like all of our equipment, the HRSG will be tripped out of service if hazardous conditions arise. Operation of the HRSG trip relay performs the following functions: bypasses gas to the stack, closes the inlet gas damper so as to isolate the HRSG from the source of heat, trips the steam turbine in the case of a single HRSG feeding a single steam turbine. So what are the conditions that will cause an HRSG trip? Typically, these will be such hazardous conditions as high steam temperature, which could damage the steam turbine internals; low water level in the steam drum, which could lead to overheating of the tubes in the evaporator section; high water level in the steam drum, which may lead to carryover and consequent damage of the steam turbine internals. Loss of a circulation pump in a forced circulation HRSG. A steam turbine trip with consequent fall in steam demand to zero. A gas turbine trip. What would happen to the condensate and feed water pumps in the case of an HRSG trip? Well, these would continue operating, supplying water as necessary. When the condensate and feed flow reduces close to zero, the respective recirculation valves will open so as to maintain minimum flow through the pumps. The pumps themselves would only trip out on loss of suction pressure or an electrical fault in the driving motor. Stopping and starting of pumps and the other auxiliaries will normally be activated by the automatic control system. The operator can override this system at any time and operate the pumps manually, for example, to test standby pumps. In normal operation, if a condensate pump or feed water pump were to trip or lose discharge pressure, the standby pump would be started automatically. Another important trip concerns the feed water supplied to the de-superheater, which, as we know, controls outlet steam temperature. This valve is tripped closed whenever the steam flow to the steam turbine falls below a predetermined minimum level. The reason for this is that with minimum steam flow, the de-superheating water, instead of evaporating, may be carried on through the steam turbine and so cause internal damage. This valve is also tripped closed when either the HRSG, gas turbine, or steam turbine are tripped. The reason is there would be no steam flow to prevent the possibility of water entering into the superheater and accumulating. Later, when the unit is started up, this water may be carried into the steam turbine. Okay, so much for trips of the HRSG, but what about control? As we have already mentioned, the exit steam temperature is continuously monitored and controlled by injecting feed water into the de-superheater. Both the superheater and reheater temperatures are controlled in this manner. Maintenance of correct temperature is very important. If the steam temperature is lower than rated value, then the steam turbine efficiency will decrease considerably. By contrast, if the steam temperature is higher than rated value by, say, 50 degrees Fahrenheit or 30 degrees Celsius, then internal turbine damage will eventually take place. The operator should always keep his eyes on the performance of the steam temperature control system and be prepared to take manual action if necessary. In the last segment, we talked about level control in the condensate and feed water system, specifically the hot well and de-aerator. They are both single-element systems. They work on a simple monitoring of the level with consequent signals to the inlet valve. Control of water level in the HRSG drums is more complicated. Each of the pressure sections has its own independent feed water control valve and attendant control system. Usually, a three-element control is used. As you would expect, the drum level is monitored, forming one element of control, and in addition to this, the control system measures feed water flow in and steam flow out. In normal, stable operation, the feed water flow into each pressure section should be the same as the steam flow out, with perhaps a correction for any small amount of blowdown. The control system adjusts the feed water control valve so as to keep the two flows in balance, but at the same time allowing the control to be trimmed by the actual drum level. This is important because the two may need to operate in opposition at times. For example, let's see what happens if the steam turbine is suddenly tripped due, say, to an electrical fault on the generator. As the steam flow from the HP superheater suddenly falls to zero, the feed water controller would try to close the feed water control valve so as to reduce the feed water flow into the HP section to zero. However, this is exactly what it should not do under these conditions. Why is this? Well, as soon as the steam flow ceases, the water level in the drum falls rapidly. Why? Well, with higher steam pressure, the steam bubbles which are in circulation in the water collapse. This is called shrink. As the water level falls drastically, the drum level monitor will override the flow elements and open the feed water control valve so as to admit more water. However, under the minor fluctuations which take place during normal operation, the three elements operate together to provide very stable control of water level. The phenomenon of water swell, that is, raising of water level, occurs during startup of the HRSG. In this case, as the water is heated and pressure is raised, more and more steam bubbles are formed within the risers, with the result that the water level in the drum rises. This increase in level can be considerable, especially if pressure is being raised rapidly. In order to prevent water being carried over into the superheater, the water level must be reduced by draining water off from the bottom of the drum through the so-called surge valves. These valves may also be called blow-down valves, but this term is usually reserved for the continuous blow-down, which controls conductivity in the boiler water. Let's look at this item. Control of the boiler water condition is extremely important, and one of the major factors is conductivity. Conductivity is actually a way of measuring the solids content in the water. Even though we go to great pains to keep the boiler feed water as pure as possible, it is inevitable that some small quantity of dissolved solids enters with the boiler feed water. Now, when this water is evaporated into steam, the solids remain in the boiler water and eventually accumulate to quite a high value. These solids consist typically of calcium, magnesium, and silica or sodium, all of which are contained in the original makeup water. A high concentration of these solids can result in two problems for the boiler: deposits of hard scale inside the boiler tubes, with a resultant lack of heat transfer, and consequent overheating and damage to the tubes. Violent fluctuations in water level, with the possibility of some water passing over with the steam into the superheater and eventually the turbine. Depending upon the operating pressure of the boiler, limits are set to the permissible solids content of the boiler water. The higher the solids content, the greater the conductivity. So, what can we do when the conductivity reaches its predetermined limit, say 10 to 15 micromos? Well, the concentration can be reduced by draining off a portion of water through the continuous blowdown. This has the effect of discharging high concentration water to be replaced by incoming feed water of a relatively low conductivity. The continuous blowdown is controlled so as to maintain the desired conductivity level in the drum. The blowdown water is discharged to waste, but in many installations the heat is recovered. The chemical condition of the boiler water and feed water must be controlled based upon regular analysis. The analysis may be performed manually on a regular basis, say once per day. In many installations, a continuous sampling system is installed to provide automatic analysis. What are we looking for? Well, generally speaking, the following constituents cause problems. Silica. A small amount of silica can cause considerable buildup of hard scale on the turbine blades, so reducing output and efficiency of the turbine. Oxygen in feed water causes corrosion both to the pipework and the boiler tubes. The pH value of the boiler water must be maintained within a narrow range, say 8.5 to 9.2. Lower pH may cause serious corrosion to the boiler tubes. With higher pH, foaming occurs. The water level fluctuates wildly and may carry over with the steam to the turbine. All of the aforementioned items are monitored and limits set. A chemical feed system is installed so as to allow us to inject certain chemicals in order to combat the effects of the undesirable elements. Typically, the following chemicals are used. Hydrazine, to act as an oxygen scavenger, that is, to absorb any dissolved oxygen which is present in the feed water. Amines, which are injected into the condensate system so as to inhibit corrosion of the steel pipework. Phosphate, which is injected into the boiler drum to control pH. Now, we're mentioning here just a few of the most typical chemicals used and the conditions monitored. Now that we have you interested in this subject, make sure that you study the requirements for your own HRSG and feed water system. This is an extremely interesting subject, but further discussion is really beyond the scope of this training program. I'm sure that many of you who have worked in fossil-fired power plants are familiar with chemical control of boiler water. It's certainly an important factor in successful operation of any boiler or HRSG. Please switch off the tape now. Thoroughly review this material in your workbook.